Number system is our topic of discussion for today from Star Academy. What we are going to talk in number system is we'll try to understand number system. We'll talk about different section of number system or different division of number system, and we'll focus on real numbers as part of this discussion or this session. We'll talk about natural number, whole number, integers, fractions or decimals, rational numbers, irrational number. We'll also talk about representing real numbers on number lines. Then we'll talk about real number Venn diagram representation, which is very useful and it really helps people to understand the concept of real numbers. Then we'll talk about transcendental numbers, and at the end we'll talk about some of the examples. So that's pretty much we are going to cover in number system. But even before I go and start number system, let's try understand why we need to understand number system. Now if you see in your day-to-day life, right from the morning till the time you go to bed, you do or you perform different activities or you perform different tasks where you make use of number system. Now couple of example could be when you get up early in the morning and when you get up ready for school, what you keep in your mind, what is the time when you have to leave from your home to school. And if your school is starting at 9 a.m., then based on where you are leaving, you plan accordingly. So this 9 a.m. itself is a place where we are using number system. You go for shopping and you buy multiple products. Now again, you can buy one product, you can buy two products, or you can buy 100 products. So this 1, 2, and 100 is again a place where you are making use of numbers. When you go for a trip with your parents, what you do, you decide where are you going, how much time it's going to take, then how much answer to this will come in terms of number system, where somebody will tell you it will take 4 hours or 5 hours and so on. So everywhere, if you start realizing the way you live your life, you make use of number system on each and every action which you perform. So it's really important for you to understand number system. Let's move on. What is number system? A number is a mathematical object used to count. As I said, how many objects you want? Do you want one object, two object? How many pizza you want? Any place where you perform, and if you try to answer of how many, what you end up is doing a counting. Then there are the different places where we use number for labels, and one of the simple example is your cell phone, where if you try to call somebody, what you do, you look at your cell phone and you dial some of the digits. Now on that digits, what has been put a label for you to understand that which section of your cell phone represent 9 or represent 8. That's one of the example where you use labels. And again, measurement, any kind of measurement which you perform, uh, again that is done through number system, whether you are measuring length of a road or length of a cloth, or if you are trying to measure height of a person, or let's say if you are trying to measure your height, but you say I am 5 feet long, or I am 5.5, or I am 7, or somebody is 6.1. So there are multiple way you perform measurement, and again there also you make use of number system. Now in mathematics, the definition of number system has been extended over the years. So it takes time for us to come to what we call it today as number system. And it was an evolving process which took years for us to come up what we talk today in terms of number system. So what you see as part of number system, 0, then negative numbers, then you see rational numbers, then you see irrational numbers, then you see real numbers and complex number. Complex number is not part of discussion for this season. We'll talk about it when we move on other discussions. But for now, this was just for an understanding that there is something called complex number or imaginary number, which also is part of a number system. Let's take some example. So number 1, 2, 3, -4, -5, 2 by 5, 3 by 8. They're all example of numbers. Similarly, if you see a square root of 2, square root of 3, square root of 15, pi, or 0.10111011101110 dot dot dot, they are all example of different numbers within number system. Let's try understanding if we look at number system, how they are organized and how we understand them. So you see any number system or any number which you came across your life can be divided into real numbers and imaginary numbers. Imaginary numbers are out of scope for this discussion, so we'll focus on numbers, then real numbers, and then further branches of real numbers. Now, real numbers can further be divided into rational numbers and irrational number. Again, your rational number can be divided into integers or fractions. Further, integers can be divided into whole number or negative numbers. Again, whole number can be divided into 0 or natural number. Now, this is pretty much a structure, or you can say different fragment of numbers, and you can look at both way. You can look at top to down approach, or you can look down to top approach. We'll talk about with some example when we move on. Real numbers, it's something which we're going to talk now. We have just understand what we mean by number, and we have seen that any number can be divided into real number or imaginary number. Now what will focus its real number now? Now real number system can be divided into different numbers, and that's what has been put into this table of what how we define them and what are the example for them. What I'll try to focus here is going through the definition of them and taking some of the examples. So if you try to see natural number, also called as counting number. So natural numbers are also known as counting numbers. And what it only include positive numbers greater than 0, but no decimal or fraction. So any number typically like 1, 2, 3, 4 as an example, what we use is known as natural number. But what it does not include 0, and it does not include decimal or fraction. What happens if you add 0 to this natural number? What you'll come to whole number. Natural number but includes 0. So when you add 0 to natural number, what you get is whole number, and it is just an extension of your natural number where you have added 0. Further, if you extend whole number by adding negative integers to this, what you get is integers. So what we mean by integers, numbers that have no decimal or fraction can be positive or negative. So what we are still not having within this number system up to integer is we do not have any decimal values added to this group, or we do not have any fraction added to this. Let's talk about what we mean by rational number. Any fraction that can be written as x by y, where x is an integer and y is also an integer, but y cannot be 0. So any number, if you can represent them in x by y, where x and y both can be integer, but y cannot be 0, we can call them as rational number. Also, decimal that terminate or repeats. Now, apart from x by y, if we transform them into decimal, or if we get into some decimal number, that can also be rational number, but we need to make sure that decimal value either terminate or repeat after certain digit. So this is what some of the example of rational number, where we have 4 by 5, 8 by 3, 1, 2 by 3, and a square root of 4. So these are different fractions which can be expressed in terms of x by y, and we can see that y is not a 0 and is an integer. Square root of 4, even though this looks like could be part of irrational number, but it's just for confusing people, because if you transform or if you simplify square root of 4, what you get is 2, and 2 can be represented as 2 by 1, where 2 is your numerator and 1 is your denominator. Now let's take some of the example of decimal number. You can also be given some of the decimal number, and you will have to identify whether they are rational number or not. Now if you check this particular example, which is 0.888888 and so on, what you have noticed that this is non-terminating decimal number, but this is repeating. So the digit 8 is repeating throughout. Now, as long as we get a decimal that either terminate or repeat, it will be part of rational number. If you check another example, which is 3.5, what you see that this is a decimal value which terminate after first digit of the decimal. If you check another example, which is 7.333 and so on, in this case also, you'll see that digit 3 keep repeating. So even this particular number is part of your rational number. Let's talk about irrational number. Non-terminating and non-repeating decimal are irrational number. So we have seen decimal representation of rational number, where what we have noticed that any decimal values which either terminate or repeat will be rational number. But if you get a decimal value which is non-terminating and non-repeating, mostly all root value of a number are irrational number, be it a square root of 2, a square root of 5, or any other numbers. Apart from this, there are transcendental number which also which also will become part of irrational number, and one of the example to this is pi. So pi is also irrational number and they are known as transcendental number. So irrational number can further be divided into transcendental number and real algebraic number. We'll talk about this more. Now, for now, let's take this particular example. I have a decimal number 0.9867594632 and so on. Now I see this is a decimal number which is not terminating, but it is not even repeating. Now since this is not repeating, I can't qualify this for rational number because any number can be treated as rational number if decimal either terminate or it repeats, like you have seen is 0.888 and so on, or you have seen in 7.333 and so on. Now in this particular case, decimal is not terminating and non-repeating, and that's why this qualify for irrational number. So any number, if you try to convert them into decimal and you get a value which is non-terminating and non-repeating, it's your irrational number. Now, if you combine all of this, natural number, whole number, integer, rational number, irrational number, what you get is real numbers. So real numbers is an universe of what we have gone through so far. Let's take an example. Natural numbers, as I said, can be repeated by n, and it's merely your counting number, which is 1, 2, 3, and so on. And then you have a number left with this, which is 0. And if you include 0 to this natural number, what you get is whole number. And then what you're left is with negative number. And if you further include this negative number, what you get is integers. And again, when you reach to that integers, what you're left with fractions. And if you include these fractions, what you get is rational number, where any fraction, if we can represent in p by q, where q is not equal to 0 and p and q belongs to integers, then we call them as rational number. Still, what we are left at this is all square root values or all root values and transcendental number. So all root values plus transcendental number are known as irrational number, and if you further combine this with rational number, what you get is real number. So that's pretty much a, a tabular view example of rational number for you to understand about real number. Now let's take an example and try to understand how do we go about repeating real numbers on number line. So one thing you should remember, any real number can be represented on number line. It's just you need to know how do you go about representing that number on number line. So if we take an example, natural number, start with the counting numbers like 1, 2 and 3 can be represented on a number line like I have shown at this place. Then again, if we add 0 to this, what we get is whole number on the same number line. And what I have done in this case, I have extended this on the left side by 1 unit to come to 0. Further, if we extend that line by 1 unit, 1 unit and 1 unit, what we get is negative integers coming on the line, and if you extend the line backward to include the negative number. So basically integers on the same line which I started with natural number, I moved it to the left to get 0. And if I further move it to the left, what I get is negative integers. And then with negative integers, 0 and positive integers, what I get is entire set of integers on number line. Further, if we try to add fraction within that integer, and fraction could be a positive integer like 1 by 2, or it could be a negative integer uh, between negative integers like minus 1 by 2, and then what you get is rational number. Further, if you add all roots within that number line, what you get is real algebraic numbers. So for example, root 2, square root of 5, square root of minus 2, square root of 5 has been added to the number line. And that's how we get a real algebraic line or value also repeated on number line. Further, if we add transcendental numbers like pi and minus e in this particular example, so it's minus pi and minus e on my left hand side, and on my right hand side e and pi, then what I get is entire real number, and any real number can be represented on number line. And that's how it completes your number line. So any number line or any line which you draw on your paper, and if you try to see that what this line can represent in terms of number, then you can make sure any real number can be represented over that line. Let's move on to the next one. Now this is pretty interesting. Now so far whatever we have discussed about real number, that helps you understanding about real number. What I've seen people understand real number more in terms of Venn diagram. And that's where I'm talking about how do we go about representing real number in Venn diagram. Now if you see here what I have done, I have represented number sets into Venn diagram. So if you look at this particular Venn diagram, the entire number system has been divided into imaginary number and real numbers. And what is our focus of discussion is this real number area. Now then for the real number, it can be divided as irrational number and rational number. And then rational number can further be divided into integers, and integers can further be divided into whole numbers, and whole number can further be divided into natural number. So if we look at in the reverse way, any counting number will give you natural number. So what it is not giving you is 0. If you add 0 to that counting number, what you get is whole number. And again, if you add negative integers to this, what you get is set of all integers. And again, if you add fractions like 2 by 3, what you get is entire rational number within this box. Now what is still missing is irrational number, which is root values or transcendental number. And if you also add them to this list, what you get is real number. So it is pretty useful for people, and especially when you try to answer questions like true and false, which has been asked, and if you get confused about providing answer, it always help you if you try to make use of this Venn diagram to answer your question. We'll talk about this with more examples when we move forward, and I'll showcase you how I have made use of this Venn diagram for providing answer to questions. There is another way through which you can represent real number system, which is some of the time pretty useful for people to understand. And this is again a good way for representation, and you can even keep this in mind. So like I'm highlighting this natural number represented by n and starting with 1, 2, 3, and so on. When we add 0 to this, what we get is whole number, and further when we add negative integers to this, what we get is entire set of integers. What is still missing is fraction, and these fraction can further be divided into terminators and repeaters. Like I have discussed in the previous slide, I said like I have discussed in the previous slide, what I said is any number which can be represented in terms of p by q or x by y can be part of your rational number. Or if you look in terms of decimal values for a rational number, what you will end up, some of the decimal value will be terminated after certain digit. However, some of the decimal value will not be terminated, but you will see that they are repeating. And since they are repeating, they'll give you a repeating decimal value or repeating digit after decimal, and that's how we call that irrational number can have two different type of fraction, one that terminate and another that repeats. Now what is still missing within this is root values, whether it is square root of 2 or cube root of 2, negative values, or some algebraic where you are adding integers with a square root. These are all example of your irrational number with some transcendental number like pi, e, log, and sine. And again, these three are probably not a good example for you to right now go through at this particular session, but definitely you would like to know about pi and e because you'll be using at multiple places. And you'll be asked questions more around pi and e where people will try to understand and will ask you pi is what kind of number. Now we often get confused with pi because some of the places we represent pi as 22 by 7, but that's not an actual or real representation of pi. It's just assumed a value for pi which we used for different calculation within different places. So that's pretty much on real number Venn diagram representation. Please make sure you understand these two diagrams as much as you can because this will really help you to crack questions on real number. Let's move to the next one. Now here, one thing which we would like to highlight is 1 by 3, which was here. And how is that a repeater? It's something which we have tried representing here. So if you see 1 by 3 was a fraction, and if you convert them into decimal, what you get is 0.33 dot dot dot, which can also be represented as 0.3 dot on the top or 0.3 pi on the top or line on the top or bar on the top, whatever way you want to call. We'll talk about this uh, in some other session in more detail, but for now let's move on. Next, we want to talk about what we mean by transcendental number. As I have said before, transcendental numbers, as an example, are pi and e, and they are part of irrational number. Now, transcendental number are some number which has been evolved over a period of time. So say for example on 1873, This was the first time when Charles has proved E was a transcendental number. Same on 1884, pi has been proved as transcendental number. So as an example, what we are looking for, we are looking to give an answer to these three questions. And we are also looking to provide reason why I think this is true or false. Take first example, every whole number is a natural number. Whether it is true or false, every integer is rational number. And every rational number is integer. Now I have to answer these questions in terms of true and false, and I also have to provide the reason why I think so. Most of you by now would have answered to these questions, but let me express this by Venn diagram. So if we are looking at our Venn diagram representation, which was 1, 2, 3, then whole number, integer, rational number, and irrational number sitting out, and then we got entire set of real number. If we try to make use of this Venn diagram, and while you are providing an answer specifically to subjective answer, you can put these Venn diagram while you are providing answer to this. That helps you to get more marks, or at least probability for you to get more marks will be increased. So let's take the first question. Every whole number is a natural number. Now we know natural number is 1, 2, 3. And we know 0 is one number which when get added to natural number gives you whole number. So when people say every whole number is a natural number is not a correct statement. So it's false because 0 is one whole number which does not fall in this block, which is not a natural number. So your first question is false, and why? Because 0 is not part of natural number. Every integer is rational number. Now if you check that entire integer set within this Venn diagram is within rational number. That itself is giving you an indication that every integer is a subset of rational numbers. So this is true statement, and we know why. Every rational number is an integer. Now if you check every rational number and take an example of 2.3, which is fraction, is not an integer. So this is a false statement. So in order for you to respond to such questions, this Venn diagram representation really help you, and you can even put this Venn diagram while you providing answer to such questions that increase your probability to get better marks, and then you can further represent this as answers like I just shown. So point number 1 was false because 0 is a whole number but not a natural number. Point number 2 or question number 2 was true because every integer m can be expressed in the form of m by 1, and so this is a rational number. Point number 3, it's false because 3 by 5 is a fraction which is not an integer. You can give 2 by 3 instead of 3 by 5, or you can give any fraction which is not an integer. Let's look some example of rational number which either terminate or repeat. So they are also known as terminator or repeaters. Let's try find decimal expansion of 10 by 3, 7 by 8 and 1 by 7. So if you try dividing 10 by 3, what you get is this number. Now Couple of things which you would like to notice on this is remainders always remain 1, 1, 1, 1, 1, and so on. And your divisor is always 3. So if you check here, when we multiply 3 by 3, we get 9, and what we get remainder as 1. And we put decimal, we get 0 here. We again multiply 3 by 3, we get 9, and we get remainder as 1. We can keep moving on and on by putting one additional 0 and dividing 10 with 3, and we'll keep getting 3, 3, 3, and so on. So in this particular case, if you notice this digit 3 after decimal, keep repeating, and this number does not terminate. So this is an example. So this is an example of a fraction which if you try to convert them into decimal, what you get is repeaters. Let's take another example which is 7 by 8. And if you try to divide 7 by 8, what you get is this. And you will see at the end, you get remainder as 0, and that's where your division ends. So this is an example where your decimal representation of a fraction number terminates. So say for example, 8, when we try to divide 7 by 8, we have to put a 0 dot and we have to take decimal representation of it, and we got 0 here. 8 when multiplied by 8 will give you 64, and if you subtract 64 with 7, what will get 6, and again you can put a 0 because of this decimal, and then when you multiply 8 by 7, what you get is 56, and when you subtract 56 with 60, what you get is 4, and then you put a 0 because of this decimal, and then you multiply 8 with 5, what you get is 40, and all of these will cancel. So this is a place where remainders become 0, and you have no need to move forward. And this is a place where your decimal representation of 7 by 8 has terminated after digit 5. Let's take one more example, which is 1 by 7, where you will see not one digit, but 6 digits are repeating after decimal. Now if you try dividing 7, if you try dividing 1 by 7, since 7 is a bigger number, we'll have to take a decimal and we have to take 0 to this, and it can be multiplied by 1 to give you 7, and then when you subtract 7 with 1, what you get is 3, and further you can put 0 and you can multiply by 4, you get 28, and then 28 minus 30, or 28 when subtracted with 30 will give you 2, and you can keep moving. When you keep moving, you'll say you'll get 1, 4, 2, 8, 5, 7, and after that you'll be back as remainder as 1, and you can see at this place if you put a 0, you will start from the same place and you can keep moving. So what you will see in this particular case, your remainders will keep moving, and even your decimal representation of fraction will keep moving. But then it follow a certain pattern where 1, 4, 2, 8, 5, 7, and after that you'll again get 1, 4, 2, 8, 5, 7, and so on. So here 1, 2, 3, 4, 5, 6. There are 6 digits which will keep repeating one after the other in this particular fraction. So that's again a repeater. This was a repeater example with one digit. This is a repeater example with 6 digits. And this is a terminator where it has terminated after 3 decimal digits. Let's move on to the next one. Now, the next one, what I'm trying to do here is I'm trying to conclude some of the things which you would like to understand. So, this particular example which we have just gone through, we have some observation. Let's make a note of those observations. First observation is reminders are either zero after some stage, for example 7 by 8, or start repeating themselves, for example 10 by 3 and 1 by 7. So you will see whenever you try to convert a fraction into decimal, your reminders will either become 0 or it will start repeating after some time. The other point is pretty interesting. The number of entries in repeating string of remainders is always less than division. Now make a note of it. What, I, what I'm saying here, number of entries in 1 and if you check repeating a string within this, it's 1 which is less than the divisor which is 3. Take this particular example where number of string in remainder was 3, 2, 6, 4, 5, 1 and it again start with 3, 2, 6, 4, 5, 1. So if you count this remainders and if you count number of entries it's 1, 2, 3, 4, 5, 6 which is less than 7 which was my division. Now same is true with this decimal value or repeating value after decimal. Now whether I look into remainders or I look into decimal values after or digits after decimal, that gives you same thing, that number of string which is repeating either in the decimal value or in the remainders will always be less than division. So even in this particular example, if you check, it's 3.333 and so on. So what is repeating decimal here is 3 and it is of one digit, which is always less than 3. Now here in this particular example, your decimal value was 0.142857 and you will again get 142857. So what you see, it's 1, 2, 3, 4, 5, 6, 6 values which is repeating and it's less than 7. So whether you look this from remainder perspective or you look this from the decimal or digit in decimal, it's always going to be less than division. The third point, if the remainder repeats, then we get repeating block of digits in the quotients. So that was the third point which I was trying to explain. So since the remainder is repeating, you will get repeating value in the quotient. So these are three different points which we can conclude by looking into this example and is valid for any other example. So the one which you have to keep in your mind is point number 2 to be sure, where example of irrational number. Decimal expansion of irrational number is non-terminating, non-recurring. Moreover, a number whose decimal expansion is non-terminating, non-recurring is irrational. Square root of 2 will give you a value as 1.41421356 and so on. So it's a big digits after decimal. And not a single place you will find the digits are following a pattern where you can say that they are repeating. Same is true with pi. If you try to convert pi into decimal, you'll get 3.14159265 and so on. We often represent this pi by 22 by 7, but this is an approximate value of pi. This is not exact value of pi. We have tried calculating exact value of pi with computer and advanced algorithm, and pi has been computed up to 1.24 trillion decimal places. Now, this is such a big number after decimal, I can't even write here on this paper. So what we see in this? Under root 2 is an example of algebraic irrational number, and pi is also an example of transcendental number, and both are irrational number. Thank you for watching my video. We have more videos on number system. Stay tuned. You can subscribe to my YouTube channel to see more videos on number system as well as more video on any concept within mathematics. Thank you.